This video will be on section 3.4, the chain rule for derivatives. And the topics in this section, we'll just learn the chain rule. This is the last derivative rule we will learn, but very frequently it is the most challenging. And like with the previous sections that just build on the previous material, when you interact or see problems that use the chain rule, you could be also asked to use any of the other rules like the product or quotient rule, the power rule, the derivative of e to the x, natural log of x, and associated things. All right, so to kind of understand what the chain rule is used for, I start by just a quick example of something. All right, so the chain rule is often necessary, but to see why we need this last rule, let's say we wanted to differentiate the following function. Say we wanted to do the derivative of f of x equals 3x plus 4 to the 11th power. Now, we've done problems where we had two things to multiply and FOIL out. So squaring, if we had 3x plus 4 squared, we could FOIL it out, get rid of the multiplication, and then do the derivative that way. Or we could also just write it squared out and then multiply by itself. We could do the product rule. So we had two ways to do that. But when it's raised to such a big power like this, it's like multiplying 3x plus 4 11 times. Now, kind of going back to the two ways we could have done the squared one, if we wanted to do this one of those two ways, we'd have to multiply 3x plus 4 times 3x plus 4 11 times. Or we would have to do the product rule 10 times. So, if you wanted to do the product rule with something like this, you would start with the first two and do the product rule. You get something new, and then do it with the third one, get something new, and then do that result with the fourth one, and so on. It would take a very long time. So the chain rule is a necessary thing, and I'll show you the formula here. It's very often not that helpful as a formula when you first see it because it doesn't really feel like it tells you much. But it deals with the composition of functions. So it says to do the derivative of f of g of x, that's what the chain rule is for, then this equals the derivative of f of x, but with g of x inside, and then on the outside we multiply by the derivative of g of x. This is what's very helpful to remember in words, and this one might be the most helpful of all the rules to remember in words, is do the derivative of the outside, keep the inside the same, then multiply by the derivative of the inside. Right. Now, you should have seen function composition before in like a college algebra class. So there is that requirement, but I'll remind you when you have a function composition like this, when you're looking at your formula, really what this is telling you is that g of x is the inside and f of x is the outside function. So that's where this inside outside comes from. That's what it says. Do the derivative of the outside, keep the inside the same, so it's still inside, then multiply by the derivative of the inside. This often is a lot more confusing until you see a few examples, and then you realize it's not terrible. It's just something you can't forget about when you do problems. It's going to look a lot like doing our rules from before, but this extra step of multiplying by the derivative of the inside. All right, so what I'll do is I'll do the derivative of my example here, the 3x plus 4 to the 11th power. All right, once again, really what you want to focus on here, how you know to do the derivative is this is not just, you do the chain rule. this is not just x raised to a power. There's something else. This could be 2x, it could be x plus 1, it could be anything inside here. But the reason that we're going to look at this and say we have to do the chain rule, this is not just x to a power. Right? If you look at all the other examples we had, whenever we had something with x to a power, it was just a number out front or separated by a plus or minus. But now we have stuff with it being raised to the power. So we're going to need the chain rule. And we'll have the equivalent things when we deal with the derivatives of the natural log and exponential functions, as you'll see when we do more examples. All right, so the inside is, kind of what you would think about the inside being. I would say the inside is 3x plus 4, and the outside, this is the one that's kind of strange, but when you do the chain rule and you practice it quite a bit, you won't actually write this out. You'll just want to practice recognizing what it is. So the outside is the function. That would be if you replace the inside with x in your function. All right, so it's x to the 11th power. Now the reason we break it down like this is we know how to do the derivative of each of these things. Right, the derivative of the inside is 3, the derivative of the outside we use the power rule. And really it just boils down to following the formula here. So f prime of x, the derivative of 3x plus 4 to the 11th power. Right, so what we do is we do the derivative of the outside. So to do the derivative of x to the 11th, that would be x, or sorry, we bring the 11 down, we would rewrite the x to the 10th power. Right, we subtract 1. So that's our power rule. But the reason I left it blank is because we have to keep the inside the same when we do this. So instead of having just x on the inside, we have the 3x plus 4. All right, so you can see how it's basically the power rule at this point, except we leave the inside the same. We brought the power down, we rewrote the inside, we subtract 1 from the power. Now this part is usually the okay part when we talk about the chain rule. When you're learning it, the easy part to forget is the ending. You have to multiply by the derivative of the inside. And the derivative of the inside, the derivative of 3x is just 3. All right, so anytime you use the chain rule, you're actually going to have a multiplication here. It doesn't matter if the other rule we're using with it is the power rule, or the derivative of e to the x, or the derivative of ln of x. All right. But once you're here, the only thing you can do to simplify is multiply the 3 times 11 to get 33, and then the 3x plus 4 to the 10th power. That would be our final simplified derivative here. Right, it does look a lot like the original one. Pretty much it looks like doing the power rule, but then like the chain rule says, multiply by the derivative of the inside. All right. Now, what your book might do, I can't remember off the top of my head, your book might tell you like general rules, like the general power rule, the general exponential derivative, the general logarithmic derivative, which are fine. One thing I would warn against is that they're all just using the chain rule. And so it feels like this section would give you 3 new derivative rules, but it's really just one. It's just the chain rule. All right, but I have them written on this next page. So the chain rule is similar to the product and quotient rules in that we use it depending on what our function looks like. So I'm just going to recall basically the 3 other rules we had for specific functions. Right? The product and quotient rule are just general. The first one here, this is the power rule. The second one here is the exponent. I'm just going to call it the exponential rule. And then the third one is the logarithmic rule. Yeah, these aren't the official names of these by any means, but just to be able to refer to them. So anytime you want to do a derivative, but your x isn't just x, like we saw with the example before, our inside, instead of having x to the power is 3x plus 4, we had to use the chain rule. When it comes to e to the x, if you have anything else in the exponent besides just x, you're going to have to use the chain rule. If you have anything besides just x in the natural log of x, it's in your best interest to use the chain rule. Although we saw with previous section that you can use log rules to simplify first and then do other things, but in general, the best idea is to use the chain rule. All right, so once again, you don't have to memorize these. These are just applying the chain rule to each of these. And then replacing x with what I'm going to call u, which is a function of x. So just to kind of refer to what I'm going to be using u as, in this previous example, u was just the inside. It would have been the 3x plus 4. Okay, but the chain rule, the general power rule, or the power rule using the chain rule, the derivative of u to the n, notice how the u and the x now are different. That's really what's going to make this chain rule happen. We still do the power rule, but we multiply by the derivative of the inside, which is the u. All right, so these are with the chain rule. You know, all the other rules we learned before, the derivative of e to the x is still e to the x and all this other stuff. This is just something we have to use sometimes, the chain rule. All right, so the exponential rule with the chain rule, instead of having e to the x, if we have something else in there that I'm replacing just by this u, we still get the derivative of itself, e to the u, just like the derivative e to the x is e to the x, but we replace it, or sorry, multiply it by the derivative of the exponent. And the logarithmic rule is the same idea. The derivative of the natural log of u, right? The derivative of the natural log of x is 1 over x, so it's still 1 over u. And then we multiply by the derivative of the inside. Right, so remember, all of these are basically the same rule. Right, if I didn't have this part here, the du over dx, these would all be the same exact rule. The chain rule just tells you multiply by the derivative of the inside, and maybe with the exponential one, you know, it might help more to think about the exponent. Okay, so that's all the chain rule is going to say, and now we'll do some more examples. But you can see how we actually used this rule exactly before. We had the derivative of our normal power rule at the beginning, right? Just keeping the inside the same. And then we multiply by the derivative of the inside. That's how it's going to work. Right, so I got an example of each here. This first one, the derivative with respect to x, and that will still match. So don't worry about them throwing you through any loops. The derivative with respect to x of 8x plus 7 to the third power. Right, now, the key here is really to recognize that you have to use the chain rule. And the reason here is it's not just x to the power, it's something with x. So we got to use the chain rule. But if you think about it like we just did before with the previous problem, we start by doing the power rule, because if this was just x to the 7th, we would use the power rule. But we keep the inside the same. But the one thing we can't forget about is multiplying by the derivative of the inside, and the derivative of 8x plus 3 is 8. Right, and once again, I'll just really point out this is the chain rule part. Right, now, if you can simplify, which we can, go ahead and do that just because it makes things easier. The 8 times 7 is 56. And the inside we wouldn't want to mess with because it's being raised to this big 6 power. We don't want to try to deal with that. Okay. But that's it for just the chain rule when you're dealing with powers. Keep in mind that anything can be inside. So if I had 8x squared, then what would be out here would be the derivative of that 8x squared. Things like that. The power can still be anything, just like with the power rule. It could be a fraction, it can be a negative number. It doesn't matter because you're still using the power rule along with the chain rule. So once again, just think about everything we're doing in this section involving the chain rule is we're doing an old rule, but then we have this new part. All right, so the second one, we want to do the derivative with respect to d of the natural log of t squared plus 3. Once again, just point out why we want to do the chain rule is because the inside is not just t. And for those of you that might think, well, I like doing log rules because I like to simplify it and then use the other one. There is no log rule for breaking apart with a plus or minus inside. So you can't actually use a log rule to simplify this. So anytime you have a plus or a minus inside a log and you need to do the derivative, you're not going to be able to break it apart. So this one, once again, we must use the chain rule. If we want to realistically do it. All right, but once again, I'm going to start with the first part. The derivative of the natural log function is 1 over the inside. Right, that's really what our 1 over x formula says. It's the 1 over the inside. And then the chain rule part says do the derivative of the inside and multiply by the derivative of the inside. The derivative of the inside is t squared plus 3, which is 2t. And once again, if you can't simplify, do that. Pretty much every time you do the chain rule with the natural log, because you're going to get this fraction over here, it's best to just combine it into one fraction. So multiply the tops together, you get 1 times 2t is 2t over our denominator of t squared plus 3. But that is simplified. You can't cancel anything out here because of the plus in the bottom. Nothing else to do. Right, and then the last one, as you might expect, the other one I want to make sure we look at an example with is with e. Well, I guess not the last one, it's the last new one. Why do we want to do the chain rule here? Well, because the exponent is not just our letter. This one, it is y, so it's not just y. Since it's not just y, there are a lot of exponent rules like log rules. Maybe you could simplify it, but you don't really want to worry about it. It's easier just to do the chain rule than try to do exponential rules and then do that derivative. Right, so exactly like before, we think about what's the derivative of e to the x? Well, it's itself. So we start with that. We just rewrite the function e to the x power, but instead of x, we have this exponent. So the exponential rule, derivative rule, the derivative is just itself. And then we multiply by the derivative of the inside. When we think about exponential functions, the inside is the exponent. So the derivative of 14y squared plus 7, which is 28y. And then, as far as simplifying this, since this is in the exponent and this is not, there's nothing really to simplify. You can leave it like this. If you prefer the 28y out front, you can move it there because it's all multiplication. But that's all you can do. Right, so once again, now you've kind of seen all three rules happen. Each time we just did the normal rule as if we had never even learned the chain rule. And then the chain rule tells us multiply by the derivative of the inside. One thing I always like to point out is if the inside was just, let's say, x here, then we would multiply by the derivative of x, which is just 1. So you get, exactly the power rule back. It's generalizing those rules. All right, but that, for the most part, that's it. With the chain rule, one thing we haven't done is we really haven't involved things that could be viewed as messy, meaning what if we just add a number out front here? Or what if we have to do the product rule with it? What if we have to do the quotient rule with it? How do we recognize which one to do first? So that's really what the rest of the section is going to be about. All right, so what we have here, number 4, we want to do the derivative of the function 4 times the square root of 4x squared plus 7. Now, one thing about derivatives is that we have those rules, power rules, exponential rule, logarithmic rule. So, we don't have a radical rule because radicals are just fractional exponents. So anytime you want to do the derivative with a radical, change the radical to exponential form. And for us, the square root function, I'm not doing the derivative. This 4 is out front here. It's not on the radical. The square root has an invisible 2 here. And the inside has a power of 1. The square root is the same thing as the 1/2 power. So just as a reminder, I don't know if we've hit it in this class yet, so it might have been a while. If we have a radical, it has an n on the radical, and the power inside is m, then we can change it to x to the m over n power. For this one, the reason why it's 1/2, when there's not a number on the radical, it's an invisible 2. That's kind of like our special rule, but the inside doesn't have a power, so it's an invisible 1. That's our normal thing. All right, but once you rewrite it like this, it should be very helpful as far as how to do the derivative now, because we have a power function, something raised to a power, and the inside is not just x. So we must use the power rule. And one thing that's different when you have fractional exponents and negative exponents compared to positive whole numbers is that there's no way to multiply it out and try to do it another way. So this one has to be done with the power rule. Right, so let's go ahead and do the derivative. So just writing it like I usually do in its symbols. Right, one thing you don't want to forget about is all our old rules. What do we do with numbers out front? Right, this part's not involving x at all. We move numbers outside of the derivative. Right, remove the coefficients outside. We can't move this 4, we can't move this 7 because it's inside the power, but we can move the 4 out front. But once again, you should have done plenty of derivatives by now to where maybe you just know that the 4 is going to hang out along for the ride. Now we want to do the derivative of the inside, and now is when we can use the chain rule officially. Technically, like I said, we could have done it here because we know this 4 is just going to stick around, but if you want to be very proper about your work, make sure you bring the 4 out so it works. All right, so we've got the 4 out front. Then when we do the derivative of this, we start with the power rule. So we get 1/2, bring the power down, we rewrite the inside, we subtract 1 from the power, 1/2 minus 1, I'll just leave that as 1/2 minus 1, and then we multiply by the inside derivative. The inside is 4x squared plus 7, the derivative of that is 8x. Right, and then the orange part, just to really annotate everything, that's the power rule that we did here. We don't want to forget the chain rule part. Okay. Now that you've done the derivative, we have no indicated derivatives left, we can combine everything. So notice that everything is on the outside of the power besides this, so we can simplify. 4 times 1/2 is 2, times 8x is 16x. And then we got 4x squared plus 7. 1/2 minus 1 is negative 1/2 power. And so, this 4, just to highlight again, 1/2 and the 8x, it's all multiplication. We multiply all that to become the 16x. And then the other part, just simplify the power. But let me go ahead and rewrite it so it's more clear that I'm saying this is the final simplified answer. And like we mentioned in previous sections, once you have the derivative, especially once you're at this point, you don't need to try to simplify it anymore. The negative exponents are fine, as we've seen plenty of times. No need to try to do anything else and potentially make a mistake. Right, and the last one is really just a similar one to number 2, doing the derivative of the natural log. One thing I really noticed over teaching this class a few times is that when you throw a number out here, people kind of want to do the product rule. But remember, when numbers are out front, they're just going to stick along for the ride like the previous problem we just did. Right. So the indication that we're going to use the chain rule here is that the inside is not just t, just like the other ones. Right, so what we're going to do, right, just like from before, the number out front is just going to stay there. Just like if we were doing the derivative of 2x squared, we would just leave it there and then eventually multiply it at the end. And what do we have here? We leave the 2. Then we do the derivative of the natural log, which is 1 over the inside, 5 minus 7t squared. So I guess I can draw an arrow. The 2 just stayed out front like I mentioned. And then because the inside of the log is not just t, we have to multiply by the derivative of the inside. The derivative of 5 minus 7t squared. Right, that is negative 14t. Right. Now, once again, you can say this is simplified but because it's all multiplication, it's best just to make it one fraction. The top we have 2 times 1 times negative 14t, negative 28t, over the denominator, which is just 5 minus 7t squared. And once again, that is simplified and we don't have to do any more to it. Right, so the other thing I mentioned is, what if we have to do the chain rule involving the product or quotient rule as well? Well, you just have to look at the problem and kind of see what goes first, and this just takes practice. What are you going to do? The product rule, the quotient rule first? Or are you going to do the chain rule first and then the product or quotient rule? Most of the time, it's going to be doing the product or quotient rule first and then just going from there. Right, so number 1, it says do the derivative of 3x squared times e to the 4x. Now, even though we're looking at this e to the 4x and probably thinking, oh, we're going to have to use the chain rule there because we're in this section, you are right. But the priority here is product rule. Since we have a multiplication, we must use the product rule first. And when you initially write down the product rule, if you do it exactly like we were doing in the previous section when we learned it, you do not even worry about which rule you're going to use until after. Right, so remember the product rule is the derivative of the first, which is 3x squared, times the second, which is e to the 4x, plus the first, which is 3x squared, times the derivative of the second, e to the 4x. Let me go ahead and just label the 3x squared as the first part, and then the e to the 4x as the second part. I don't want to cover the exponent though. All right, so we can more easily see that this should be the product rule. Now, exactly like we were doing the product rule before, after we write it down, we do the 2 indicated derivatives. And this is where you might see the chain rule pop up. You still might only see the old rules pop up without the chain rule. But right, it's just the same setup. Exactly like we did last section. If we weren't even in this section, we haven't brought up the chain rule, we would be doing it exactly like this. Right, so the derivative of 3x squared is 6x, and then multiply by e to the 4x plus 3x squared. And then the derivative of e to the 4x, we must use the chain rule here. That's the new part. This is the only new part in this problem. We must use the chain rule here because the exponent isn't just 4. Or sorry, isn't just x, not 4. Right, and so to do the derivative of e to the 4x, we, derivative of e to the x is itself, so we just rewrite itself. And then we multiply by the derivative of the inside, the derivative of 4x is 4. And that's what the chain rule gives us for that part. Okay. The first derivative we didn't need the chain rule because it's just x to a power. The 3's out front, so it stays along like always. But this part we needed the derivative to use the chain rule. Right, but once we're here, we've done all the derivatives. Now if we can simplify it, go ahead. The first part we got 6x e to the 4x plus the second part. If we simplify it, we got 3x squared times the 4 is 12x squared. Then it's times e to the 4x. And like when we were dealing with this before, you can really stop here if you want, but you can factor quite a bit out. So the 6 and 12 have a 6 in common. The x and the x squared have an x in common. And then we can also take out the e to the 4x in each part. When we factor that out, we actually factored out the whole thing in the front, so we're left with a 1. And in the second part, the 12 becomes 2. The x squared, we took out one of the x's, so it's still x, and the e to the 4x is gone. Now you don't have to do this part, it's up to you. Either one of these is good. But the one on the right that I have in blue might be the answer you see in the homework. And if you have something like this and you get it wrong, you might think that you're totally off. But either one is correct. They're both the same thing. All right, but I would at least get to here, I would at least simplify this part, the 3x squared times the 4 to the 12x squared. This makes it a little easier to type in the homework as well. Right. So number two, we want to do the derivative of ln of 4 plus x, then divided by x to the 5th power. Okay. Now, for the same reason as the last time, I don't really care necessarily what else is going on at the beginning, except that there's a fraction. There's division. We're going to use the quotient rule. And the quotient rule, remember what that says is we do the derivative of the top. So the derivative of ln of 4 plus x times the bottom, x to the 5th, minus, right, it starts off looking a lot like the product rule, because we have a minus. Then we write the top times the derivative of the bottom, and then divide it by the bottom, which is x to the 5th squared. Right, and just like every time we did the quotient rule last section and like the product rule above, we do the two indicated derivatives and just kind of go from there. And I'll also remind you that when you deal with the quotient rule, typically we just leave the denominator alone. This one we can simplify a little bit, but leave alone until the end. Once the numerator is simplified, maybe we can simplify it a little bit, but other than that, leave it alone. All right, so the derivative of the natural log of anything is 1 over the inside. Let me not write that in purple. So we got 1 over 4 plus x. And this one's kind of funny, I think, because the derivative of 4 plus x is just 1. So it kind of is going to look like we didn't even use the chain rule because the derivative of the inside is 1. So that's the derivative of the natural log of 4 plus x. The 1 is the derivative of 4 plus x. All right, then we multiply this by x to the 5th minus the natural log of 4 plus x times the derivative of x to the 5th. That's just our ordinary power rule. That's 5x to the 4th. And then we divide it by x to the 5th squared. This is something we multiply the exponents and we get x to the 10th. Go ahead and box that in. All right, so I'm going to clean this up a little bit. So over here on the left part, this is all multiplication. If we multiply the tops, we get x to the 5th over 4 plus x minus the part on the right. It's just a matter of order of multiplication. We can move the 5x to the 4th in the front or leave it in the back. It's up to you. I prefer it in the front, but that's just my preference. All over x to the 10th. And then one thing you can actually simplify here is you can factor out an x to the 4th in each term. And the reason why I'm pointing that out is because I know eventually if we factor that out, it will be able to be canceled a little bit with the x to the 10th. Okay, so I'm going to factor out the x to the 4th on the top because it's in both terms. When we take out the x to the 4th in the front term, we have 1x on the top remaining over 4 plus x. And then in the second term, the whole x to the 4th is gone. So we got 5 times the natural log of 4 plus x. All over x to the 10th. And this is really the one example where you will do something with the denominator. Right, normally we'd be done here. The top is simplified, even though it's very messy, it's simplified. But now we can cancel out because this x to the 4th is out front. Right, we can't cancel out if it's just in any one term, but it's out front. We can cancel x to the 4th with x to the 10th and make it x to the 6th. 4 of the x's are gone. And so our final derivative answer here, we got x over 4 plus x minus 5 times the natural log of 4 plus x. And then that's all over x to the 6th. Right, still pretty messy. But what canceling this out does is it at least makes there a little less stuff involved. If you did have to plug in a number, let's say, if you had to plug in any number at all, even though it'll work out to be the same number, it's just a little more simplified and easier to deal with. All right, so really that is the chain rule. One thing that I think is kind of nice, this will be sort of an introduction into chapter 4, but seeing it once is useful before then, and it's something that we can do now, so we don't actually need to be in chapter 4 to do it, is this following problem. It says find the derivative and the values of x where the tangent line is horizontal for f of x equals the square root of x squared minus 12x plus 43. Now we already kind of did a derivative like this, although we'll definitely do it out again. But the first thing to point out is it kind of gives us a different question than we're used to. It's asking us where the tangent line is horizontal. Well, what is this really telling us? Horizontal lines have slope 0. So what this is really telling us is to find the x values where the slope of the tangent line is 0, which is what we call the derivative. So find the x values where f prime of x is 0. And if you recall from last section, we actually did a problem like this as well. but it told us directly find the x values where the derivative was 0. This is just giving us a different way to ask that question. Right, but the first things first, in order to do this anyway, we'd have to do the derivative, so let's do that. Right, what I'm going to do is just like before when we dealt with the square root, is rewrite this as the 1/2 power. Oops, minus 12x, not plus. So always rewrite the radicals as powers when you're dealing with derivatives. Right, so we start by doing the power rule, which means we do 1/2, bring the 1/2 out front, rewrite the inside, and then subtract 1 from the power. Since we did one like this before, I'll just remind you that 1/2 minus 1 is negative 1/2. Right, so this is the power rule part. And what we cannot forget is since the inside is not x, we must multiply by the derivative of the inside. So the derivative of x squared minus 12x plus 43. And the derivative of x squared minus 12x plus 43 is 2x minus 12. Now, if we were just computing the derivative and nothing more, then we could stop here, maybe simplify it a little bit. Since we want to find the values where f prime of x equals 0, one thing I want to do is talk about the negative exponent real quick. Right? If we want to make this exponent positive, we know what we have to do is bring it down to the denominator to switch the sign. And when you're actually working with derivatives, it's a good idea to get rid of them. If you're just plugging in a number, that's fine because the calculator can handle it very easily, but we're not just plugging in a number, we're trying to solve something. So since we are trying to solve something, what I recommend is get rid of negative exponents. And the way we do that is, since this one is in the top, we must bring it to the bottom, bring it to the denominator. Now on the off chance you had a negative exponent in the denominator, then you'd want to bring it up to the numerator. All right, so we have 1/2 here. What I would say is just stick the thing inside here, the x squared minus 12x plus 43 to the 1/2, just bring it down with it so visually it looks like this, that's fine. And then we have a multiplication of 2x minus 12. And yeah, I'd go one step further, like we did with a lot of the other problems when we did derivatives of logs, we got a lot of multiplications of fractions. Just go ahead and make it one fraction. Right, so when you deal with actually working with derivatives, you want to simplify as far as possible. So 1 times 2x minus 12 is 2x minus 12 over 2 times x squared minus 12x plus 43 to the 1/2 power. Now there is one thing you could do. This is entirely optional. This is simplified, but if you want to factor the 2 out of the top and cancel it with the bottom, that's fine as well. So I'll say this is simplified enough, but we can do one more step. And that one more step is to factor the 2 out of the top. When we take a 2 out of x minus 12, we get x minus 6 over the bottom. And then we can cancel the 2's out. And we are left with our absolutely as simplified as possibly can be derivative of x minus 6 on the top over x squared minus 12x plus 43 to the 1/2. And I'll tell you right now, this cannot be simplified anymore. You cannot do anything about the square root for simplifying. Even if the inside was to factor, the square root really makes it hard to do anything with it. And the top x minus 6 is simplified. There's nothing to factor out there. All right, so it's not a bad habit when we get to chapter 4 and we're dealing with doing stuff like this in almost every problem, to practice simplifying completely. Even if, I would say even if you type this as the answer in your homework and it will mark it correct, try to get to here. Now you still get the credit, but just practice getting it to here. All right, so that's part A, and then part B, we want to now find the x values when f prime of x equals 0. And we actually dealt with problems like this before. When we did it before, there was also a fraction. When you're trying to set a fraction equal to 0, really all you care about is when the numerator equals 0. All right, because if we set the whole fraction equal to 0, what you end up doing is you end up multiplying to get rid of this. But when you multiply it to the other side, it multiplies by the 0 and it goes away. So we get 0 equals x minus 6. Add the 6 to each side, and we get x equals 6. And that's our only answer. And one thing I like to do with this one, since we actually found a value where this graph, the tangent line is horizontal, the slope is 0, what I like to do is just graph it and see, can we actually tell? Because this will be important as well. So what I will do is I'll graph the function, the original function. I don't care about graphing the derivative because, ultimately if we made a mistake there, then our answer is going to be wrong. So we want to graph the square root of x squared minus 12x plus 43. And I'm going to hit zoom in the standard Windows 6. And what a horizontal tangent line is going to look like is, think about the tangent line. It's kind of the line that has the slope that's just touching it. And where are we at x equals 6? Oops. I need to hit the graph. So what I will do is calculate the value at x equals 6 so you can see where x equals 6 is exactly. And if you drew this tangent line, since it's kind of flat here, this tangent line is actually going to be horizontal. The slope will be 0. One thing that will be of a lot of interest in chapter 4 is when the slopes are 0 or D and E. And at least when the slopes are 0, very often they look like this, where they are flat. Either it looks like it's at a minimum, it's at the bottom, or it could be the opposite way at the top, and it could look like a maximum. Right, but that's just a little preview. And also what the slope being 0 looks like, the derivative being 0 looks like for a function.